So let's do chapter 15, problem 7 and 9. So we're on page 410. And we'll do number 7. So the problem reads, calculate the Schwarzschild radius of the Sun. Now by Schwarzschild radius, we mean that if you have a certain mass m and it has a certain radius r as a sphere, then if you send out a photon of light, then that photon of light will not escape. It will be turned around and come back to the source of gravity itself, because the gravitational attraction is so strong. So you need an immense gravitational attraction to have this happen. Now the escape velocity of an object is given as the square root of 2gm over r, and in this case the speed is the speed of light, so we change v to c, and it's the square root of 2gm over r. And if we square both sides, then what we see is that c squared is equal to 2gm over r, because the square of a square root is just the object itself. So if we multiply both sides by r and divide by c squared, then we see that we have cancellation here of c squared, cancellation here of r, and we get r is equal to 2gm over c squared, which is the Schwarzschild radius. Now the gravitational constant g is in the back of the book. So it is equal to 6.67 times 10 to the minus 11. So 2 times 6.67 times 10 to the minus 11. And we are calculating the Schwarzschild radius for the Sun, and the Sun has a mass of 2 times 10 to the 30th kilograms. And we have to divide that by the speed of light squared, which is 3 times 10 to the 8th, times another 3 times 10 to the 8th. So now we do a little bit of arithmetic. And at the top we have 2 times 2, which is 4, times 6.67, which is 28, times 10 to the minus 11, times 10 to the 30th. On the bottom we have 3 times 3, which is 9, times 10 to the 8th, 10 to the 8th, which is 10 to the 16th. So we have 28 times 10 to the plus 30 minus 11 is plus 19 over 9 times 10 to the 16th. And 9 goes into 28 about 3 times, so it's about 3 times 10 to the 3rd meters, which is about 3 kilometers. So the Schwarzschild radius of the Sun is about 3 kilometers. So if you shrink the Sun down to a sphere that is 3 kilometers in radius, then light will not be able to escape from it. So the next problem that we go to is number 9. So we're on page 410, number 9. And a reading of the problem. Use Wien's law to determine the wavelength of light generated by 10 million Kelvin degree gas in an accretion disk. What type of photons have this relationship? Wien's law says that lambda max times the temperature is equal to 2.9 times 10 to the 6, as long as the wavelength is in nanometers and the temperature is in Kelvin. So if you divide both sides by T, then you get that lambda max is equal to 2.9 times 10 to the 6 and over the temperature. And the temperature is given in the problem as 10 million, which is 10 times 10 to the 6. So you see you get a very nice cancellation of 10 to the 6, so that lambda max is equal to 2.9 over 10, which is equal to 0.29 nanometers. So now if you go to the table way back in chapter 4 on page 110, then you see that at the top of the page, using the diagram there, that 0.29 nanometers is clearly in the range of X-rays.